All right, so we decided to spend an extra day on Chapter 7, so I thought that for today's pre-lecture video, I would do some example problems of using the conservation of energy, both when it's conserved and when we have non-conservation due to forces like friction. Okay, so our first problem is pretty much a classic roller coaster. So we have a roller coaster going through the hills and valleys of the ride. And we're told that at point A, it always has a mass of 80 kilograms, but at point A, it has a speed of 20 meters per second. And the vertical height at that location is 200 meters. The first question is, what is the total mechanical energy of the roller coaster at point A? Well, it's going to have both potential and kinetic energy at that location. Its potential energy is related to its Y position above the ground. We already were told what our reference point is. It's at the bottom. And then kinetic energy is 1/2 mva squared. So this is simple substitution. And our answer ends up to be 1.73 times 10 to the 5th joules when we add our two terms together. Part B is actually pretty easy. It says, what's the total mechanical energy of the roller coaster at point B? We actually were told to neglect friction, so energy is conserved. That means that the amount of energy that the roller coaster had at point A is the same as the energy it has at point B. The only difference is when it gets to point B, at B, all the energy would be kinetic. And that's because the height at B, is 0. All right, so let's continue the problem. Now it wants to know what the speed of the roller coaster is at point B. So we can say the energy at B, which was 1.73 times 10 to the 5th joules, is equal to, all its energy was kinetic at that location, so we just set that equal to 1/2 mv squared. We're going to divide by the mass, and we take the square root of all that. And that gives us a velocity of 65.8 meters per second. So it's going pretty fast at B, but we expect that because all its energy is kinetic. Finally, the speed at point C, the energy at C is equal to that it had at B and at A because energy is conserved. But at C, it has some potential and it has some kinetic. So the potential is mgyc plus 1/2 mvc squared. So we can solve for the speed there. And so we could just substitute in here. So I've rearranged this all in one step to solve for the velocity at C. First thing, I would multiply the whole thing through by 2, divided by the mass, and then took the square root. And our speed ends up to be 34.5 meters per second. And so all this kind of makes sense if we think about it. The lowest speed was at point A. That's where it had most of its energy and potential. Of course, it was going the fastest at B because all of its energy was kinetic. And then at point C, it had a speed that was somewhere in between. The next problem is a conservation of energy problem as well, but it's a little tricky because we actually end up using components in this problem. So we have a projectile being fired at an angle of 40 degrees with a speed of 30 meters per second. And we know that this is going to go up to some height and then come back down. What we're asked, though, is we want to find the speed when it's at half of its maximum height. So we want to know this is y max over 2. Now, we did something similar the other day when we had the ball that was initially shot up in the air, and then we wanted to know how fast it was going at half its height. And we said, well, only half the energy gets converted into potential energy. So it initially started with all kinetic, and half of that kinetic energy gets converted into potential, and we could use that to figure out the speed. The problem is here that the initial energy, which is kinetic, what we have to remember is we have to think about what's happening to the velocity for a projectile when it's shot at an angle. Keep in mind that v squared can be thought of as a combination of the x and y components. But for a projectile, vx is a constant, and it's equal to whatever it was initially. That's what we learned back in chapter 3, I think. So the x component of the velocity remains constant. The y component is the one that changes. Because as the object goes higher and higher, the y velocity will go down. So at the top, Vy is equal to 0. So what we're going to say is, instead of half of the total energy going into potential, if it was just vertical, we only are going to have half of the energy associated with the Vy. Okay? So, first of all, let's find out what these initial velocities are. V naught x initial is going to be 30 times the cosine of 40 degrees. And that was, I thought I had calculated it, 22.98. And V naught y is 30 times the sine of 40 degrees. And that turned out to be what was that? I got it. So, sorry, didn't write that down originally. The original V naught y is 19.3 meters per second. And so what we're going to say is, so there's an initial piece of the potential energy. So the initial energy is 1/2 m v naught x squared plus v naught y squared. But what we're only interested in is this piece right here, because half of this will go to potential energy when it reaches y max over 2, when it reaches half of its maximum height. So that's what we're going to be working with. So the energy that we have is 1/2 mass times v naught y squared, and we're going to take half of this will be equal to the energy, the kinetic energy that it has at the halfway point. So what we've done is this amount of energy, this energy right here, half of it went into potential, goes into potential and half of it goes into kinetic at that halfway point. And so we want to figure out what the speed is, and this is what we're looking for. So I got 1/2 times 1/2 m v naught y squared is equal to 1/2 m v at 1/2 squared. The m's cancel out, one of the halves cancels out, so v at 1/2 is equal to v naught y squared over 2 square root of that. And that turns out to be 13.6 meters per second. But the question was, what was the speed? So we don't know. The speed is going to be the square root of vx squared plus vy squared. In the previous slide, I had said that vx squared was 22.98, and we just found the vy squared is 13.6. So our velocity, what we were trying to find, is 26.7 meters per second. So that one's a little tricky because we had to use our knowledge of projectiles. We did break it down into components. I don't want you to think that there's like a x and a y component of the energy. What you should think of it was a certain fraction of the energy that was being available to being converted into potential energy. It's a little bit different, so it's a subtle difference. And now the last one we're going to deal with is when there's friction. When there's friction, energy isn't conserved. In fact, it's lost. So conservation of energy says that the change in kinetic plus potential is 0. This is not true here. Here, the change in kinetic plus the change in potential is equal to the energy, oops, sorry, I can't spell, energy lost because of friction. Sometimes we think of it as the work done by friction. And I like this idea because this really represents the final minus the initial. And this emphasizes that the final amount of energy is smaller than the initial, and this is why this is going to be a negative quantity. It represents the fact that we lost energy. So the problem here specifically is we have a box sliding on a rough floor. It's going to be moving with a speed of 1.2 meters per second. It's going to hit the spring and compress it 5 centimeters. During this time, work done by friction is minus 0.5 joules. That means that's how much energy is lost. And so we have delta K plus delta U is equal to minus 0.5 joules. This is 1/2 mv final squared minus 1/2 mv initial squared, and then plus our change in potential energy. We'll look at this in a minute. Now our final velocity, what happens is it's initially moving with 1.2 meters per second. It's going to compress the spring, and when it does, it comes to a stop. So the final velocity is actually 0, so it doesn't have any final kinetic energy. The initial kinetic energy is associated with the speed of 1.2 meters per second. Once it compresses the spring the whole way, it has a potential energy of 1/2 kx squared. It didn't have any initial potential energy. So what this ends up simplifying to is 1/2 mv initial squared plus 1/2 kx squared is equal to minus 0.5 joules. In this particular problem, what we're trying to find is the spring constant, K. So we're going to rearrange this to solve for K. x is 0.05. That's because we have to change it into meters from centimeters. It's the amount the spring was compressed. If we do plug in our values, we get a K of 1,040 newtons per meter. The second part of the mass, what is the coefficient of friction between the box and the rough surface? Well, the work done by friction, which was minus 0.5 joules, is equal to the force of friction times the distance that the friction acted through. Remember, the force of friction is going to be mu times the normal, which, because of this was on a level surface, is just going to be mu mg. So we can do some substitution here. Mu mgx. Mu is going to be minus 0.5, sorry, this is minus here too, over minus mgx. And we get a coefficient of friction of 0.41. And that's it. So those were our examples to one pretty simple conservation of energy problem, one conservation of energy where it was a little tricky, and finally one problem where we had to deal with friction and its effect on the conservation of energy.